Entonces, es graduada en matemática, tiene la maestría en matemática con énfasis en estadística pelo Instituto Nacional de Matemática Pura y Aplicada, INPA, en 87. Tiene el doctorado en estadística por la Universidad de Washington, en Seattle, en 94. Es, fue profesor del Departamento de Estadística de la Universidad Federal de Minas Gerais, pero actualmente es profesor del Departamento de Ciencia de Computación de la misma universidad. Su especialidad es en modelos estocásticos, con énfasis en estadística espacial y está envolvido en aplicaciones en demografía, ciencias actuariales, epidemiología, economía y otras áreas. Él es editor asociado de la revista Biometrics en International Journal of Health Geographics. Renato tiene más de 100 artículos publicados, 2 libros, 14 capítulos de libros, supervisionó cerca de 40 maestrías y cerca de 10 doctorados. La charla de hoy, en alguna manera, refleja su actual envolvimiento en la área de computación. Entonces, Renato, lo ves.
Muchas gracias, Pedro. I'm gonna switch to English because my Portuñol is not as good as yours. But thank you very much for the introduction, and I want to also to thank the Instituto Interamericano de Estatística, especialmente Silvana Specona e Pedro Moretin for this invitation to talk tonight. I'm gonna share my screen to start showing my slides, and I hope you can see my slides now. Is it okay?
Yes.
Okay. And I will not be seeing the chat. So if you have any question, please just open the mic, the microphone, and you can interrupt me at any time. Also, just to add, besides the Universidade Federal de Minas Gerais, where I keep a faculty position, I'm also working at this company, ESRI Incorporation. We produce the ArcGIS, a major software for data analysis of spatial data. And I have been there for 3 years now. But well, the topic of my talk is Monte Carlo, the new methods of Monte Carlo simulation. Many statisticians are not aware of these major advances we have been having in these last years. In fact, simulation now is done in a way that it's never seen before. It's really amazing and impressive what we can do nowadays. We can generate very complex objects such as such as images of human faces. These are all faces of people that do not exist. These are people that has been generated by Monte Carlo. The usual Monte Carlo simulation, we just generate random numbers like uniform 0-1 numbers, mix them up, and this type of faces appear. Or we can create images of landscape. This has been done in using the DALI, the image generation of ChatGPT tool based on prompts. I ask for a urban scene near the ocean. Or we can create images in the style of Van Gogh paintings, new texts as if it was written by Jorge Luis Borges, or we can create songs, simulated songs in a certain style. Well, this modern Monte Carlo methods, all of them are based on deep neural networks. They are very powerful and practical, but they must be based on deep neural networks. There is no other model that has been able to produce such similar impressive results. So classical statistical methods or classical simulation models is not able to do are not able to generate this type of objects that I showed previously. However, the main ideas of these modern Monte Carlo methods can be understood without deep learning knowledge. So that's my aim here, to explain what are these main modern Monte Carlo methods without going too deep on deep learning. So let's start with a very short history of Monte Carlo. And it starts, well, to generate a random variable x, a univariate random variable. We learned how to do this in 1948, almost, in fact, during the Second World War in the Project Manhattan, the Manhattan Project in Los Alamos, where people were building the atomic bomb um, in with the help of John von Neumann, Stanislaw Ulam, and Nicholas Metropolis. We developed the main modern simulation Monte Carlo methods that are used until today. One of these main, of course, all of these others here are well known by statisticians, but Stanislaw Ulam is very important in many ways. It participated in the Manhattan Project. It started the project to build thermonuclear weapons with Teller. Introduced the concept of cellular automata, created the Monte Carlo method, proved a series of theorems and proposed math conjectures. And there is this wonderful chapter in this book of Giancarlo Rota. You can find it here in this link. And it describes Stanislaw Ulam. It's Giancarlo is a mathematician and he's a wonderful writer. So it's really worthwhile to read and what he has to say about Stan Ulam. And this is a letter from von Neumann to Stanislaw Ulam. And in a way, it's really almost a birth certificate for the Monte Carlo methods. It's a two-page letter. It's written in Princeton, in the Institute for Advanced Study, where von Neumann was living at that time, to Stanislaw Ulam. It's 1947. The war was over. And then here is the first paragraph with personal issues. And then he said, well, I'm very glad that preparations for the random numbers work are to begin soon. In this connection, I would like to mention this. Assume that you have several random and blah, 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 and then goes on explaining. And then he says, this is, as I see, the method that you have in mind. This method is the one, is the inverse transform that I will describe soon. And it's a method that we use until today to simulate data, random numbers. And then von Neumann goes on and say, as an alternative, which works with the variable x, and all values of the density line between 0 and 1 is this, and blah, 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 blah. And this is the second method, the main second method that we use until today. And it's just this. It's just 4 lines here in this letter. So the second method may occasionally be better than the first one, and he describes when this goes on, and it describes here until now, and then it finished saying that, well, the method may still be worth keeping in mind, especially when the ENIAC, one of the very first computers, is available. And then he ends. So this is in 1947, and soon enough, the method, the Monte Carlo method appears as a paper in our JASA journal. and by Metropolis and Stanislaw Ulam. John von Neumann is so big, so huge that he is not even an author in this paper. This is amazing. I mean, it's the founding paper of the Monte Carlo method, and he's not part of it, although he's clearly one of the authors of one of the main methods of generation of random numbers. So the Stan Ulam method is a very simple one. Suppose, well, there is the generation of uniform 0, 1 numbers is is a very specific and technical method that I'm not gonna describe here. Is really a deterministic method that fools and passes all type of statistical tests to check if there is a pattern of generation of these numbers. So when it passes all these statistical tests, very strict tests, then we consider them as being pseudo numbers that looks like uniform in 0, 1. The problem is, given that we have a generator of numbers between 0 and 1, real numbers between 0 and 1, how to generate all the other uh, random variables or all the other distributions that we know of. Well, the idea is, given that we can simulate and generate a random numbers in this vertical line here between 0 and 1, and uniformly so, imagine that we want to generate a random variable x with a certain cumulative distribution function f, just shown here as this line. So if we generate a number, a random number in this vertical axis, then we can go back and find the inverse. This is the z, the random number, and then we come back and see a random number x, which is just the inverse transform of this random z number. So x is also random, implied and determined by z. So the fact is that the distribution of this X number generated in this way, where the only random thing is the number generated here on the 0, 1 on the vertical axis, this number that appears here randomly has exactly the distribution given by this cumulative distribution function. So that's the method that Ulam had. So the idea is deterministically transform using this the inverse cumulative distribution function the z number, which is a uniform 0, 1. So for Neumann, he has a different method, the one that I showed in 4 lines, and he says that you can generate almost any distribution, not the target one, with a different method. We accept some, reject some of the numbers that we generated, and this is basically the acceptance rejection method proposed by von Neumann on those 4 lines. Then sometime about the same time, these other guys here, they propose a different method, which is called importance sampling. As for Neumann's ones, it can generate from almost any other distribution, not you generate, I'm sorry, you generate numbers from basically any other distribution, not the target one, and then you accept all these numbers from this very different distribution, but you weight each sampled value according to its importance. So these are very old methods. They were created almost in 1948. So it has now about 70 years old. The multivariate distribution of random variables has the same principle and was created about the same time by the same group in the Los Alamos during the Manhattan Project. So MC is basically generated there. That Metropolis guy who was working in Los Alamos is responsible for the Markov chain Monte Carlo method. Well, the initial versions of the Markov chain Monte Carlo method. And then we can generate this a vector of numbers, not one single univariate random distribution, and they are correlated ones. It's more complicated, more difficult, but the same principle, the same ideas are behind that. However, what we want and what we have been able recently is to compare this type of simulation here random numbers with this other kind of image. So what we can do now is to create entirely new, previously unseen example through probabilistic simulation. And these examples are examples of objects highly structured, very much structured, such as a human face. So a human face has to have a nose, a mouth, ears, hair, and it must look realistic. And that's exactly what we can do here. So these are people that do not exist. These are just based on random numbers. And that's what I'm going to explain. Before we do this, let's just make this fun thing here. I have two pictures here. One is from a real person, and the other one has been created by just grabbing a lot of random numbers, mix them up, and then creating this fake image of a person that do not exist. So can you tell them apart? Which one is the real one? So in fact, I don't know exactly. This one is just an image that I fixed. So if we look here and go directly to the web page, we can see now. And it asks us to click on the person who is real. Anyone can try the left one, the right one. Go on, people. Open the audio and make your choice.
The right one.
Is the real one. Let's see. So yeah, you are correct. The right one is real. So let's play it again. So immediately generated two. One of them is real. The other is a real person. It's a picture from the internet. And the other one is just a fake person that do not exist, created by simulation, the Monte Carlo simulation. So which one is the real one? Don't be shy.
Left.
Left. Yeah, you are correct. So good. 100% of if we ask a monkey which one is the true one, 50% of the time he will be getting right. So we have a better we are having a better score right now. So which one is the real one now? Okay, I will imagine that maybe because of this details here, it's not a clean face. Maybe this one is the real one. Let's see. Yeah, we are correct here, but let's try it again. Oh, there is something strange here near the ear. So maybe this one is the real one. Yeah, we are correct here. Though I think I'm playing this game so many times that I'm starting to get a good one here. Oh, there is some details here on the back. Maybe this is one, the real one. Yeah. Well, we are having a very good score here. But what I want to say is compare these two images. I mean, look at this one. This is a person that do not exist. Can you tell this? I mean, this is really very realistic. It seems like almost unimaginable that you could create something so realistic like this with just using 1 million random numbers. So GAN is, I'm going to explain how it works, but GAN is the nickname that we have for this first method that I will describe. Suppose that we want to generate a highly structured random object, such as a human face. The idea is select 1,000, 1 million. We want to create this human face as an image, 1,024, 1,000 pixels or elements on the horizontal and 1,000 in the vertical to create an image here as a picture. So it's 1,000 by 1,000, so 1 million, basically 1 million random numbers. So we start by selecting 1 million random numbers, uniform random numbers between 0 and 1. Every time that I say a pure noise here, I'm talking about a uniform random numbers, independent uniform random numbers. So you generate 1,000 of them in each one of these plots, and then in each one of these separated noise images, you mix the random noise numbers in a deterministic way. This deterministic way is just passing through a neural network. It's just a linear combinations, divisions, and so on. So we just make combinations of these numbers here. And the aim is to generate a realistic human face associated with each one of these noise images, like this. So we just grab these numbers, pass through a deterministic function, and that's the result. Now we're going to pass through the same deterministic function, but as the random numbers are different, we create a completely different image here. Same thing here. We start with completely random numbers, pass through the same deterministic function, and we get a completely different image here, just changing the random numbers. Now, this is the cartoon that's when a lot of formulas and then a miracle occurs, and that's the result. So let's try to be a little bit more explicit here in this step about how this miracle occurs. So GAN, a very short history, is that is the acronym for Generative Adversarial Network. It was introduced at NIPS, a conference in computer science and machine learning in 2014. So it has exactly 10 years now. And it by this guy, Ian Goodfellow, this guy here, and Joshua Benjo, his advisor at the University of Montreal. And this is the paper. The paper. Of course, there are other people here working and helping in the paper. And how it works. Before we start with the mathematics and the description, the technical description, let just me give the intuition of how the GANs works. So we start with a data set of examples. The examples are the objects that we want to simulate, similar objects that we want to simulate. For example, the examples could be instances of the instances of random object could be a collection of cat images. So we want to generate images of cats in different positions, of different colors, in different ways, as I showed here, different types of human faces. So if my examples, my initial examples, are rich enough to contain different cats, types of cats in different colors, in different positions, and so on, I will be able to learn how to generate them with the GAN. So I start with the collection of images, or it could be a collection of a more rich image like cats and dogs. So two types or two classes of objects, dogs and cats. And, it has to be a very large collection, but it could be a collection even much larger than just cats and dogs, could be a collection of animal images in very different species. Or the examples could be a collection of audio files representing songs because I want to simulate songs. Or it could be a collection of texts like news or papers. So it has a large collection of this type of texts. I will be able to generate a new random object that looks like a text, like the Jorge Luis Borges text that I showed before. So we get this very large data set of complex real-world examples. And I consider them to be IID instances of a random object coming from a certain probability distribution. This probability distribution is completely unknown. I don't know exactly how to generate images of animals. And the objective is to generate new instances, new examples that could be real. We should be unable to verify that they are simulated examples. They will look so real, so realistic, that we will not be able to differentiate between the real examples that I will use to train and fix and fit my neural network model. My simulated examples, they will appear real world examples. So most of my examples and description will be based on images because it's easier. But as I showed before, the examples could be songs or audio files, could be texts, but I will concentrate here most of the time with the with image, because the fundamental ideas are the same for different types of objects, although the type of neural networks that we need to consider in each one of these different type of objects is different. So I want to give some examples in specific details more. And because of that, I decided to select the image as the main example during this presentation. So let's imagine that we have data of each example, and this is we create a random vector X representing this data. For example, for image, we can just collapse this image 1,000 by 1,000 in a long vector of 1 million positions, 1 million entries. Assume that the examples are IID random vectors with a certain probability distribution, P of X. And now comes a giant if. If P of X is known, except for some perhaps few parameters, and if it is not too complicated, we have the remote possibility of generating new examples. In practice, P of X is amazingly complicated, of high dimension, and worse yet, is completely unknown and high dimensional. So GAN comes out as a solution to simulate data based on this sample, on this large collection of examples coming from a certain probability distribution that we don't know what it is. So in GAN is a game between two players, a game in the sense of game theory from mathematics and coming also from von Neumann, the same creator of Monte Carlo method. So GAN is a game between two players. One is called the generator, G, and the other is the discriminator, G. The generator is responsible for generating new examples, as similar as possible, yet distinct from the known examples in the training data set. The discriminator is, because it's a game, it's an opponent of the generator and responsible for detecting if an example is fake, if it is created by the generator, or or if it is a real example from the data set. So the most relevant is that the GAN learns how to generate from that unknown distribution P of X based only on the examples that supposedly are coming from this P of X. And of course, it learns that with a certain neural net model that we're going to describe. So let's start to understand how this GAN as a game. So each example is seen as a random vector. X has a certain probability distribution, P of X. The density is unknown and high dimensional. And this density does not vary during the game and does not depend on the player's actions. It's just based on whatever the nature makes to create, for example, faces of celebrities. So the game has two players, the generator G and the discriminator G. And we have a sequential game with alternating actions. G acts, and then D, then G again, D, G, and so on. So the generator G, G in fact is a neural network to simulate data. It produces a data, I'm calling it X hat, just to differentiate from the real data that is called X. And this X hat is obtained by transforming a random noise vector Z by a deterministic function G that has to be learned during this process. So G is a deterministic, a fixed function that is going to not change. I will have the work of getting this G and learning this G. But after I do this, it's like a fitted model. The model is done. Now I can use the model to predict new values. So I grab a Z, a random variable, random vector, pass through this deterministic function, and I get here this simulated value X hat. So the randomness is only here on the Z. G is fixed after I learn how to fit a neural network model to my examples, my data set. So G aims to produce examples, X hat, that follows the same probability distribution of the real data set. The ultimate goal of G is that this X hat are indistinguishable from the real ones. We are not going to be able to distinguish between the real face or the fake face, as in that game that we saw. In its turn, G during the game, it's a sequential game. G plays and then G and then G again and then D, the discriminator and so on. So when G has to play, it produces a random variable X based on this G through Z. So a random variable Z, I transform it with G, and then I get X hat. So G is a deterministic function that is determined somehow. We will see how we do this later. And as the game progresses, G keeps changing, adapting, and improving, because in my initial steps, G will not be a very good one. I will learn how to get a very good G that will be able to generate good faces, human faces here. But in the beginning, I don't know how to create this G, so I will just grab some random parameters here. So G will be a really lousy generator in the beginning. But as the game progresses, G will be keeping changing, adapting, and improving. And how exactly this happens, we will see shortly. So G and D takes turns, each playing in their turn. So imagine that we fix a size for a mini batch of examples, like 32. When it's the generator's turn, it produces 16 fake images, half of the mini batch, like 16 of fake examples. So we generate 16 Z values, Z vectors, I'm sorry, transform each vector by the G, grab then 16 fake images, X hats. And when it's D's turn, D is presented, the discriminator, the other player, it's presented with a mini batch of 32 examples. Half of these examples are real examples. You just selected from the data set, the large data set of real faces, human faces that I have in the beginning. I select 16 of them randomly to pass on to the discriminator. And also, he receives another batch, 16, again, the other half, 16 fake examples with the generator. Whatever the generator is at that moment in the game. Remember that G will be improving during the game, but at any moment with the current specification I have for G, I created my fake image and I pass them to the discriminator. So the discriminator has a task to infer based on this mini batch of 16 fake images and 16 real images. He has to discriminate between them, has to tell which ones are real, which ones are the fake one. And how this is done? Well, it is going to use a function D that gives the probability that X is real. X here is an image that could be a fake one or a real one. So based on this function, it's not clear how it's going to create this function, but right now, just keep this for a moment. When having this function, it evaluates if the function is greater than half or smaller than half. If it's large, then it says that it's real. The probability is large of being real, so I will say that it's real. If the probability is small, that the image that I have is a real one, so then I will predict that it's a fake one. Of course, the discriminator, its aim is to obtain a function d of x, the probability that x is real, such that it has a very close number, is very close to 1 when the example x is real, and if x is a fake image, then it says that d of x is close to 0. gives this value of close to 0. So in each step for D, we are using this mini batch of 32 examples, 16 real, 16 fake, created by the generator that it's current at that moment. And then D has this binary classification problem. He has to find a good model, the D model here, this probability, to separate out the two groups of data, the real versus the fake one. For example, imagine that this D of X here is based on a logistic regression based on the X vector entries. The X vectors, imagine that this black image faces an image of just gray values. So numbers between 0, 1, given if the pixel, the element of the image is very close to 0, or if it's very is black, or is white, or in the intermediate. And suppose that based on these vector entries, I just create a logistic regression. I mix them up with a linear combination of these pixels, and then I try to say if it is real or not. Probably this logistic regression will not be a very good one. But in principle, I could use any type of classificator, statistical classificator here to discriminate between the two groups using the image pixels elements to try to differentiate between the two groups. So in each game step, D gives one numerical step towards the MLE of the logistic regression model. Supposing that it's a logistic regression, the one important difference from standard statistics here is that in this game, when it's D turn, he tries to go close to the MLE, but it doesn't go all the way to the optimum, to the maximum. It just gives one numerical step during the numerical procedure for usual logistic regression. He would just give one step. And why? I mean, so there is no need to find the MLE at that moment in one step here. And why this is so? Well, because the MLE will be another value in the next turn of the game. Remember that this is sequential. So here the discriminator receives a bunch of fake images created by the generator. He has to try to discriminate them too with this function. And as soon as he gets, one step in the direction of being a little bit better in improving and getting better to discriminate them, then it's the turn of the generator. And he changed his generator to try to fool the discriminator. So whatever he finds in the previous step, it has to be changed again. So because of that, and to accelerate the convergence, because both of them has to converge and be good players in this game, we don't go all the way to find the MLE. We just gives one numerical step. And so basically that's the main reason. But we don't really use logistic regression. What we really use are deep learning models for this type of problem, because logistic regression will not be able to discriminate between, dogs and cats images. So how exactly is a GAN descriptive schema for images? Imagine that the images here are this classical MNIST model where we have each one of these digits here represent one image with numbers between 0 and 1 representing the gray scale in the pixel. And so these are the images. And here is the discriminator. The discriminator has to discriminate between images that are real, like these ones, which are I just go on the data set, I select a mini batch, like 16 images, and I'm going to pass this to discriminator with the labels that these are real ones. They are the ones. And here are the zeros, are images that are created by this generator. I'm going to explain this generator in a bit. But this generator here, it creates this fake image, and these are passed to the discriminator with the label, with the y variable, what the response variable equal to 0. So the discriminator here has to try to end here with that d of x images. For each one of these examples, he has to say, is this real or fake? What is the probability that the image is real? And that's the discriminator. So before we go on in describing the generator and discriminator, let's just comment here about the game and some of the questions. G is trained to deceive the discriminator. They are adversaries in this game. G must create fake samples that are indistinguishable from the real ones to the discriminator. D must be able to distinguish real samples from these fake samples that the discriminator is producing. So the first fundamental technical questions are how to obtain the function g of z that the generator uses to produce fake examples. How to obtain d of x to discriminate between real and fake examples. Then we need to answer the question, does this work and why? Silvana, I'm seeing here that it's 7:50, and I forgot to ask you for how long should I talk?
No tenemos 3 horas para usar, con lo cual no tiene una restricción. No sé cuánto tiempo más necesita para terminar la exposición.
Mas media hora, 30 minutes.
Bueno, sí, de acuerdo.
Okay. Yeah, I'm going slower than I was thinking. Okay, so is this generator is really possible to generate human faces based on random numbers z? Yes, it is possible. Suppose that the image, we do have a probability distribution that can generate human faces. So if this is the cumulative distribution for all the pixels in the image, and disjoint distribution, it can be always written in this way with breaking down in these conditional cumulative distribution functions, then we can just generate an equal number of random values, IID uniform 0, 1 numbers, and then get that Stanislaw-Ulam method to invert these uniform numbers to generate x1, x2 that follows exactly that cumulative distribution function. So in principle and theoretically, yes, it does exist a function g that takes noise z as input and transform them to x with the whatever desired density you have. So this g is based on this inverse of the cumulative conditional distribution functions. The problem is that these functions are not available in practice. We don't have that because first of all, we don't have the joint distribution. And even if we do have a joint distribution, probably it's extremely difficult to get the cumulative distribution functions and the inverse ones, the cumulative of the conditional ones. So the solution then is to imagine that this very complicated function that exists, it can be approximated by a neural network. There is the famous theorem of universal approximation of any function by neural network. If the neural network is, dense enough, deep enough, then what we're gonna do is represent g of z as a neural network which has parameters theta g will be the weights and biases of this neural network and its architecture. We infer or learn the parameters of g using the large data set of examples. So we have these two neural networks, g and d. So the discriminator here, as I mentioned before, we get from the training set, the real examples and some fake images created from random noise by the generator. We pass this to the discriminator. It's here. So what is this discriminator? For image, imagine that we just have to classify into two classes, the fake and the real ones. We need to learn the parameters of the neural networks with the mini batch of images composed by half a real, half a fake. In principle, we could use any statistical classifier for discriminate between the two groups of objects, logistic regression, random forest, SVM, but we really use a neural network. None of these other methods here will be able to operate in this type of examples and complex objects. So what is the discriminator then? What is this neural network? Is successive layers of spatial moving averages. Because we are working with images, the typical architecture will be successive layers of this neural network, where in each layer, basically, we pass a spatial moving average we move here on each one of the images to create a summary of this image. And the weights of this weighted average will be learned by the process of fitting a neural network to the data set. And the objective is that passing this spatial averages here and here, at the end, we get a very good idea of which ones are the real ones, which one are the fake ones. Now, what is the typical architecture of the generator? Here's the training set. Here is the fake image that I will pass to the discriminator, and this has to be created by the generator here. So what is this generator? It starts with the Z, the random noise, and at the end it has a structured image. For image, the generator receives this noise vector. Suppose it has a dimension of 1,000 random numbers. So what is G of Z? What is the generator? Is a series of successive layers of what we call upsampling CNNs. CNNs are convolutional neural networks, are again spatial averages on top of the Z that creates this block here, and then we upsample to make it a larger image, and then we upsample again until we get this. And how we do this, it has to be learned by the process of fitting the neural network. So that's the type of generator for the image. Now, how to do this? The code is very simple. Here is based on the Keras, one language to do this. This is doing exactly generating here, defining this generator that I showed before. The discriminator is similar to that. So maybe I'm gonna see here the time for I'm gonna go a little bit faster here. Just remembering that we have a data set with human faces in each step of this dynamic game. In the discriminator turn, D takes one step towards the MLE fit of a neural net parametric model. It has this parameters theta of D, the discriminator, and the output of this neural network is this binary, is this probabilities, this number between 0, 1 that given the parameters of the neural net, gives the probability that that image that we are providing to the discriminator is real. So how we gonna do this? The discriminator is a good discriminator is one that is able to separate out the real and the fake ones. How we gonna fit this neural network? This is easy, very easy. Yeah, indeed, it's very easy for the discriminator. Because it's a classification problem between two classes, a binary classificator, we can easily write down a log probability. I mean, given that we have a and number that gives the probability that it's real depending on parameters, we can write down the log probability of observing the zeros and ones in our sample when we have this model. So we write down this log probability, the log likelihood of having those zeros and ones, depending on the parameters of the neural net. And with this log likelihood, we just get the minus this log likelihood and call this the cost function. That's the usual terminology in GANs. But it's just the log likelihood is the negative of the log likelihood. And then we find a neural net parameters theta d that minimizes this cost function. We calculate the derivatives of the log likelihood and can give one step towards the maximum or the minimization of this cost function. So the cost function at the end is exactly like a log likelihood for a logistic regression. So, but this d of x, rather than being a logistic regression probability, is the output of this neural network. We sum over the real image the log of the probability of being real, and for the fake ones, the zeros ones, is the log of -1 minus the probability of being real. And we have to minimize with respect to the parameters of the discriminator of the neural net. Just to make this more explicit, we're going to put this this probability here as depending on these parameters of the neural network of the discriminator. So this is the cost function for the discriminator, and then a good discriminator should minimize this, and then we can do this with numerical procedures. Now, what should be the cost function of a generator? That's when the genius of Ian Goodfellow, the creator of GANs, came. Because the discriminator, given that it has to discriminate between those two types of objects, if you can find some function that tries to discriminate it in some way, it's not difficult to write down a function that should be minimized in getting then a good model to discriminate between the two groups. Could be a logistic regression. But for the G, what is a good model to generate real faces of humans? How to minimize a function that at the end will get parameters that say, well, now this function is able to grab random numbers and create a real face. This is not simple. This is not easy. So that's when he has this great genius idea. He's going to use the game theory because he's going to imagine that he has this play between the two, the discriminator and the generator. And the loss of one of the players is the gain of the other player. And the sum of the two losses is always zero. So it's a zero-sum game. So given that he has the loss function for the discriminator, the loss function of the generator should be just the opposite of it, the negative of it. So this is the loss function of the discriminator. So the loss function of the generator should be just the negative of that, such that the sum of the losses is always zero. Whatever one loses, the other gains. So we need to minimize this loss with respect to theta g. But where is theta g? Because before I express it this variable here, and there is no theta g. There is no parameters for the generator here. Where is it? Is it there? Yes, it is. Because remember that the fake images are created by the generator, which is a neural network with parameters. So the fake x is this solution of this g of z, where g is a neural net and z is just random numbers. So the discriminator function that I had before, which was this one, it has to be changed here in this term, in the second term, because when x is fake, in fact, x here is of the form g of z, where g depends on theta g, the parameters of the neural networks. So now I can really express the cost function as depending on the both parameters of the generator neural network and the discriminator. And as before, the cost function of the generator is just the negative of with the same cost function, but for the discriminator. So in practice, then to solve this and to get good estimators for these two parameters, we use a numerical procedure. And the numerical procedure is that we start with completely initial random numbers, and then we alternate the two steps. We fixed one of the parameters, for example, the generator, and we update theta g. And the other way around, we fix theta g and we get an update for the theta g. With luck, this procedure converts, and with great luck, it converts to the minimax solution of a zero-sum game. And these updatings that I'm mentioning here are made using stochastic gradient descent. So we just calculate the theta g, for example. This updating is whatever current value we have for theta g, and then with a certain constant here, epsilon, to not give a too large step, of times the derivative, the gradient of the cost function based on the mini batch composed by m numbers of with respect to the theta g. So this is just the derivative of that cost function in these parameters. Same thing here for the theta g. So we alternate between these two numerical steps. So now coming to examples, so that's enough for the theoretical part of the very loose description of the method. But this description that I made of this vanilla GAN, it can be adapted in different ways to different tasks. This one here is very simple. It's just creating new anime images. We start with a data set rather than human faces. It's just anime faces, and then we can create new ones. And you have the code here, for example, if you want to play with this type of simulation. Or now it comes how quickly people start to think in different ways to use that idea of the GAN. Here, the idea is that the input, the data set that I'm going to start with, is composed by a pose and the image. It's a person like this one, and a scheme of a pose that I want to have the person in the position with. So the idea is that this is the person, and I want to see this person in a different position, in a different pose. Something like this one here. That's this dots, this blue dots is just position points in their body. And based on that, I want that you grab this picture and generate this other one here. So that's what the GAN is able to generate. So my inputs, rather than just a bunch of data sets of human faces, I'm gonna now provide as input a pair of two things. One is an image of a person like this, and a desired position for it represented in this way. And he has to learn how to simulate data in this target position, like this ones here. These are the simulations. So it's very different. It seems like very different from the GAN that I described it. But if you go on and look exactly what it does, is basically just changing a little bit the loss function that I presented before. And here is another example of just adapting the GAN for a slightly different type of cost function. Here is making a transfer. So we start, the input is given one type of image, and I want to create another different type of image composed by, for example, this is the scene of zebras. I want now the zebras to become horses. And that's the other way. So I need here a data set of pairs of images composed by zebras and horses, different zebras and horses. And now I want to that the GAN learns how to pass from one to the other. For example, note here this one. This is a horse in this green field. Now I create a zebra, And because the data set are zebras in typically African savannas, the savannas are typically not as green as this one, this landscape here. Because of that, because of what it learned from the data set that I gave, he says, well, I'm going to put a zebra here where this is this horse, but the landscape has to match the type of landscape the zebras goes on. And that's why this becomes a less less greener landscape, a more gray one. A different type of the same GAN here, the style transfer, is the one where we give a picture, a real photo to the GAN, and the task is to create to change this picture to an a painting, a picture, no, an image that represents a painting in one specific style of a given painter, like Monet, for example. So here are the images of um, real landscapes transformed in paintings of Monet, of Van Gogh, Cézanne, and others. Here's is a different one, still with GAN, the same type of Monte Carlo generation, but here is a little bit different because what we do is we give a sentence and then several images are created based on that sentence. So like this one, this flower has long, thin yellow petals and a lot of yellow enters in the center, and then it creates this image here of this Portuguese is girassol, sunflowers. Okay, so there's a few other examples that I'm going to change and skip, otherwise I would take too long. And now just to finish, I will not be able to describe in any detail possible, what are two other methods that have been becoming very popular in these last 3 years, normalizing flows and diffusion models. So I'm just present here examples and the main idea and how different it is from GANs. In fact, I decided to spend most of the time with GANs because it's more different from normalizing flows and diffusion models. Normalizing flows and diffusion models, these other two methods, are more similar to the classical Monte Carlo methods, although they still use deep learning models at the end. So suppose we want to generate the MNIST digits, like this ones here. Each image here is one digit, and we want to learn and to do this. We can do this with GANs. So how normalizing flow works? Oops. Ooh, I skipped this. I I think it's at the end. I think I changed it, the order here. I'm sorry. I'm sorry. I'm going to start with the diffusion models. So the diffusion models, the idea is that to start to make a model to corrupt an image until it ends up with pure noise is very easy. We just grab an image, and each one of the pixels, we add some noise, and then we add more noise, and then we go on like this. At the end, we have a completely noise here. Imagine that if we can learn how to do this, is easy to do, and we can easily find the distribution of conditional on X on the initial image. We can find the distribution of Z if we know what type of noise we are adding. So the Z's here, conditional on X, is easy to obtain the distribution of all these vectors, the successive images. Now imagine that we can also, and that's the nice thing, we can revert the process. We not only know how to get the final distribution of the noise here, starting conditional on X, but we do the other way around. We can revert this process and find the distributions on the other direction. And that's exactly what is behind these diffusion models. And these are examples generated by the ChatGPT, the DALI model. We can just give a prompt, a sentence, and it creates an image that represents that text. So it's not only an image, but an image connected and conditional on this text. Same thing here, just a different example, creates again with the same prompt. And we can create videos. Probably, maybe you have seen this. We just wait here now. Not only a static image, but a video with a level of realism that it's amazing. It's very realistic. But this is completely fake. It's a woman walking down the streets in Tokyo. So now, just really finishing, as you see that I'm not really being able um, to um, uh, to spend any time on describing the models. And in fact, I think I lost here the slides from the normalizing flow, but my time is really up. And just to finish, and this is such an impressive methods that I could not resist to start making my own work in this area. And I'm still learning, and the area and the topics they change with a speed that is I never seen before in my life. Is always when you just learn a few things, it's just gone, and people are doing new things and different things, and so. But I have been doing like this one is we are using GANs to do clustering of images. Imagine that you have images of different things that you don't know, for example, different animals or different types of images, and you just want to create a clustering, make a clustering, separate out in different groups, but you don't know how many groups there are and what they are, and it's not a classification problem. So we did this, and this has been presented in the top artificial intelligence conference recently. Um, then we did some work for optimization of the neural networks, improving some of the methods, some of the optimization methods is again in a very important. Computer science, as you know, it's based on conferences. Papers are presented in conferences, not in journals, and they are always. And some of this work is just not out yet. Um, we working with some Petrobras, the oil company in Brazil. We are doing some GANs to measure similarity between oil profile of the oil well logging data that collects with sensors on the walls of the oil's wells, um, the different porosity or density, different types of measurements. And what we want to is to measure the similarity between an oil well represented by, for example, four of these sensors measurements. And here is the copula method that is well known for statisticians. We are the copula methods typically ask for one specific class, like Archimedeans ones or Clayton ones. So you have this, you always find copulas within this type of classes. So here we are using copulas to approximate transforms that are copulas, but completely non-parametric ones. So not fixed in one given class. If you want to go deeper in these topics, this is the book that I recommend. It's relatively new. I think it's come out last year. Yes, on December 2023. It's very recent. You can find a PDF on the author's web page. It's free. You can download or you can buy the hard copy. It's very good, very well is written, and I think it's user friendly. And that's all. I'm sorry if I took too long, but the topic is really fascinating. I like it very much, and I hope you also enjoy what I could show you today. And with this, I come back to you, Silvana.
Pedro, may I ask a question?
Sure. Claro.
Well, good evening, everyone. Renato, nice to hear you yet again. Always great to
Hello,
listen to you.
Paulo.
Thanks for the nice talk. Renato, two things. I was wondering on the adversarial network, on things like we are used to discuss statistics, stopping criteria when you judge that the image is okay, and assessment of that.
Oh, there is two things. One is the convergence is when the discriminator is the generator is such that it generates images and the discriminator cannot discriminate them all. So when the d of x, the probability that x is real, is equal to half or approximately half for every x, any x, then that's when you got the convergence. So that's the optimal discriminator, and this also represents the optimal situation for the generator. And basically, we try to minimize this, go on with the numerical procedure until we get something similar to, d of x close to half for everyone. But convergence is not simple in GAN. And that's, in fact, one of the reasons that GAN is becoming less popular than these other two methods, the diffusion models and the normalizing flows, because they get better convergence results. So GANs are great when they work, when you can really get a good data set and you can get the things working, you get the type of examples that I showed here. But it's not always that you can. It takes a lot of fine tuning, a lot of time, and it's not just great. And also, there is this problem that you mentioned, that how to numerically evaluate the quality of what you are having. Let's say, I mean, when we made the play here, it's about trying to discover which of the faces was real and fake. We, as humans, we could easily see that the quality was very good. It's really hard. It's really difficult to discriminate them. But when we have a more sophisticated problem, like trying to get something painting as a Van Gogh, how to really check and verify that that thing is good enough or is better than some other um, model that does the same thing. Only qualitative in a qualitative way. So all these issues are issues that are theoretical and have been research topics in these last years. But thank you very much for the question.
Thanks, Renato. Thanks, Pedro.
Renato, there is a question of Margot Adriana, which is the following, which is teaching strategies you can use to teach these simulations to students who are in the first, or who have the first probability course.
Yeah, Margot, well, there are several different flavors of courses in the internet, and here we are in UFMG. We have been now, I think it's the fourth year. For 4 years, we have been teaching every semester, either for graduate students or undergraduate, 2 different courses. All these topics, deep learning and this part of modern Monte Carlo simulation that I had to rush here. And I think for someone who has only very basic probability knowledge, it's difficult to really grasp. It is possible, but I think it's not, it requires certainly knowledge of mathematics, calculus, and linear algebra. Certainly, a lot of linear algebra would be very good that the person not only has probability, but also some feeling for data analysis and at least some simple statistical models like regression models, for example. Fitting data at least with regression models, parameter estimation, evaluation of quality of fit. And so these would be requirements for taking a course like this. I think with only basic probability, it is possible, but I think would be difficult because then we have to, typically in one semester, 60 hours, and so would be too much to learn. I mean, these other prerequisites would be necessary, I think. That reference that I showed, that book gives a very good way. I mean, I think it's very user friendly. It's a very good balance between theory and practice. It has lots of computer code in the website of the author. So everything that is taught in the book has the code, the corresponding code is his web page, and has lots of exercises. So I think there are many other books, but I like very much this one. And then looking at that, you can see more clearly what is required for the student. Yeah.
Okay, there is another question by Enrique Nieva. What are the different types of neural networks that can be used in conjunction with GANs? And how do they contribute to the generative and discriminating process within the GAN framework?
Well, typically the type of neural network changes very much depending on the type of data that you have. For example, if you have text, then typically you're not going to use that CNNs, the convolutional neural networks that is more specialized for images. Convolutional neural networks basically imagine that you have an image, a matrix, and then you go on with doing a spatial average of the pixels to grab and summarize what you get in each piece of the image. It doesn't make much sense for text to work in this way. It's not a planar data set, and it doesn't make sense. So for text, it's considered to be a time series, a long time series, and then it works. The type of neural networks is called recurrent neural network. It works exactly in the same way we work with time series. I mean, for each position or for each word in a text, it looks in a neighborhood of that word to see what it should use to predict that word. The major type of neural network that was discovered for text is called transformer. And oh yeah, let me put here in the chat. I forgot to put there. There is two places where you probably blue, one brown, three blue, one brown. Huh? Is this one right? There is this website is a website with many mathematical videos that is pretty much like artwork. It describes neural networks in a very beautiful way, in a visual way, and also the transformers and what is behind the ChatGPT. Transformers is the major and state of art nowadays. So all the other recurrent neural networks are gone, and we basically use transformers in this attention mechanism. They say is attention mechanism is basically a way to, rather than fixing what is the window that you have to look in the past to look and save, like a Markov, imagine a Markov model where we look at the 5 previous steps to predict the next one. So rather than doing this, it's kind of open, and you can go as long as in the past, longer in the past, or look at it as a smaller window. Is how long you go is exactly what is the attention that you need to give to these previous words, and this keeps changing, and it's kind of flexible. It's a very nice idea that Google did, and that what is behind the amazing power of ChatGPT. But I don't work with text, but it's that. So the neural networks are changing depending on the type of data that you have.
There is another question. Can you see it?
Yeah, it doesn't work. It's fine. It's strange. Are there repositories of the methods presented today easily accessible? Yes, I mean, because what I presented is Pedro and Silvana, if I can send a link for these slides, because most of the slides has the links for some of the examples that I showed. They are you have in the GitHub the code and the data to reproduce some of the examples, like the anime generation, human faces. But yes, and also in this textbooks, for example, it gives a lot of references and pointers for uh, reproducing all these GAN examples. And seems to be one other here. I found very yeah. Well, if you like Andrea Salles, go on with that references that I showed here. Is the book by Simon Prince. Is if you can find it in like Simon Prince, and you get the you can let me
There is
share
something on the chat.
Yeah, if you just type Simon Prince and where is the zoom here? My goodness. Oh yeah, here. Let me just share my window again. See, if you go to this web page, just type deep learning and the name of the author, Simon Prince, like Principe, Simon Principe in English. Then if you go here, you will find not only the notebooks to run all the examples that he has in the book, but also you can download the entire book, the PDF here. And so it's 500 pages, but then it goes on describing like loss function, maximum likelihood, and no, it's a very good book describing. It's very well done. I like it very much. So binary classification. So everything that I discussed here, what I did is basically concentrated here on this normalizing flow. I didn't have the time to the GANs, generative adversarial networks, normalizing flow, and variational autoencoder is a variation of GANs, and diffusion models. It's here. So what I described here are 4 chapters of this book. But then if you go there, you can reproduce the results and with the images and the notebooks, simple examples and more sophisticated ones like those. And these are run using Colab, Google Colab. Everyone learns using Google Colab to run these models in GPTs.
Thank you so much. Really interesting book.
Okay. One thing that I would like to mention is that when you mentioned, for example, the convolution, the CNNs, you said that they are very good to image. That's true. Then you said that for time series and sequences in general, you use recurrent networks.
Right.
And mainly the LSTM networks.
Yes, LSTM was a method that was very popular until
Yeah.
recently when these transformers came out.
Used. Yeah.
Transformers is from, I think, 2020.
No,
Transformers, attention. This was a paper by this attention is 2017. 2000
Yeah.
Attention is all you need.
All you need.
This
Yeah.
paper came out and it started to make some noise, and people start to realize that it was a very powerful for treating time series. So LSTM is a much more complicated method than transformers. Transformers curiously is simpler than LSTM and gives better results, much better. So nowadays, people are not using LSTM anymore. It's hard, Pedro, because as soon as we learn, so like for example, I spend a lot of time learning GANs, and GANs are becoming less popular now. I think the idea is still great. I love it, and I'm still trying to explore. But now everyone is moving to diffusion and normalizing flow, and you can see when you go to the conferences that where 3 or 4 years ago everyone was doing GANs. Now perhaps only 25% of the papers in this simulation stuff is on GANs, and all the others are diffusion and normalizing flows.
Yeah, that's true.
It's very fast.
If any other person don't have questions.
Someone asked here, I saw better, one of the questions is about if they can use R to, yes. In fact, the Brazilian one who is responsible to transferring most of the, some of the platforms, like especially the Keras that I showed here to R. What is his name? I'm forgetting now. I gave you the course, a mini course with him I'm forgetting now. But yeah, so in R, yes, you can find and you can run some of these examples in R. But most of the more complex examples are people use Python, and some of the platforms in Python, PyTorch especially, to run and fit the deep learning models, transformers. And so typically you will find software, but not directly in R. It's better if you really are serious about this to learn Python and PyTorch.
Okay, if there are not any more questions, we thank you, Renato, for the nice presentation. Very nice.
Thank you for the invitation to you and Silvana and the International Institute, the Inter-American.
También quiero agradecerle a Renato. Excelente la presentación, realmente muy interesante. Y bueno, se nota por el interés que ha despertado la audiencia. Muchas gracias por dedicarnos este tiempo para el Instituto de Estadística, para ampliar los conocimientos de sus miembros. Y muchas gracias, Pedro, por moderar esta conferencia.
Muchas gracias.
Muchas gracias.
Gracias.
Bye.
Buenas noches.
Buenas noches, muchas gracias.
Buenas noches.